All right, good evening. We have a really interesting presentation on reducing perchlorates in the Martian soil by Sojin and Mark Zottola. And so please begin, Sojin, when you're ready.
Thank you. So I would like to start by briefly introducing myself. My name is Hajin Yu. I am from South Korea and I am a high school student. So I don't have accomplished careers like many other speakers at this convention. And what I'll be presenting is a research that I've done with my chemistry teacher at my school. His name is Dr. Zottola. And it is about reducing perchlorates in the Martian soil using metal and borohydride complex. So I think we all agree that our ultimate goal is to create a self-sustainable habitat on Mars. And by self-sustainable, I mean that we have to be able to, it has to be independent from the Earth. So independent from the Earth's help and its resources. We have to be able to use the resources native to Mars, be able to transform it into a usable form, and make the whole process repeatable so that it's self-sustainable. Now, I think one crucial task here is to find a sustainable means of producing food, because food is so relevant to our and directly relevant to our survival. However, for this task, perchlorate poses a challenge. Two Viking landers have revealed that the Martian soil is contaminated with 0.5 to 0.8 percentage perchlorate, and perchlorate is known to be a toxin. So 3 problems of perchlorate. First, it inhibits the thyroid functioning. It inhibits the uptake of iodine by our thyroid, and also disrupts the process of producing hormones, which are central for regulating our body's metabolism. The second problem is that a study has revealed it significantly reduces the size, chlorophyll content, root length, and oxidizing power of plants. And the third problem is that it is very mobile in aqueous systems and it accumulates in plants. So the contamination is pretty widespread. And since it accumulates in plants, we humans as eaters of those plants are affected. These problems all point to the fact that removal of perchlorate is needed. Now, prior to our proposal, teacher Mark and I remembered that perchlorate is a known oxidizing agent. It is used in manufacturing explosives and propellants. And since the central chlorine atom is surrounded by 4 very electronegative oxygen atoms, it is a very strong oxidizing agent. And so we thought we could find a reducing agent to put it in a simple redox reaction and attempt at a reduction. And from our organic chemistry class, remember that borohydride is a very strong reducing agent because of the 4 boron and hydrogen bonds, which are highly polarized. And so we attempted to study the interaction between borohydride and perchlorate, see if they get involved in a formal redox reaction. To test this idea, we used computational methods and then proceeded into wet chemistry to validate our results. So I used some quantum mechanics calculating programs, which is the Firefly QC program, which is based on the game's US source code. And on this program, I attempted at reacting perchlorate with borohydride. And to be more specific, I used the function p3lib dp and to study the potential energy surface of this interaction. And this means that I looked for the points at which the molecules found the most stable, the most energetically lowest point. And in a chemical reaction heads towards the state where the molecules are the most stable. So this method would give me the final product of that redox reaction. And in addition to all of this, we use the game theory to study the bonding between perchlorate and intermediates. Our initial attempts to form compounds with perchlorate and borohydride was actually unsuccessful. And this was predicted because perchlorate and borohydride are both negative anions. And so their electrostatic repulsion would create a barrier which is hard to jump over. And so this was a very reasonable result that indicated we needed counter ions, the positive ions, to sort of mitigate the repulsion and coordinate the molecules. So we chose to involve some divalent metal cations such as metal, magnesium, and zinc. And from now, I'll briefly go over the output files, the results that we have encountered from this process of calculating things. First result, we tried at coordinating the metal ion with perchlorate. And so, as expected, we saw that they coordinated very well. And here's a table reporting the distances, the bond lengths of each bond in this complex. If you look at it, the perchlorate molecule alone would have chlorine and oxygen bonds that have lengths of 1.5. However, when we added a metal cation and coordinated it to the perchlorate molecule, we found that the bond with the chlorine and the oxygens adjacent to the metal significantly lengthened, so it reached an average of 1.6, whereas the chlorine and oxygen bonds next to them actually shortened, so it was about 1.4. And this was a result that indicated that the metal ion actually sort of disrupts the perchlorate structure. We looked at some more details to see this interaction. We looked at the charges. The first table shows the charge of the central chlorine atom in each complex. And the second one is the electron density of each bonds in this complex. If you look at the charges, I'll just look at one set of data at this game. There are different methods and they show the same results. I'll look at the first column. If you look at it, for perchlorate alone, the central chlorine atom would have a charge of about 2.3. However, when it was complexed, it increased, and so it became less negative, indicating a charge depletion on chlorine. And along with this change, we observed that if you look at the electron density sort of means the strength of the bond. We could see that the bond between chlorine and the oxygen next to the metal, their electron density sort of lowered, so the bonds weakened, whereas the other chlorine-oxygen bonds, they had higher electron density, and so they had stronger interaction. And next, we tried something very important, and it is to test the effect of solvation. And the reason we did this is because the whole reaction takes place inside a solvent, the water solvent. And it was necessary to see how the water molecule would sort of change affect the interaction. And when we look at the bond lengths, there is only a very minor difference. And we did see a minor weakening, so the lengthening of the bonds, but there wasn't much change. There was big enough to shift the entire configuration of the complex. Next, we added another water molecule next to perchlorate. And here's the point where things started to get really interesting, because if you look at it, so prior to all of this, there was almost a near perfect symmetry in the perchlorate molecule. So the bond length of the chlorine and the oxygen next to the metal was pretty much the same. But at this point, when we added the second water, we saw the symmetry break. The chlorine-oxygen bond, anti-periplanar to the entering oxygen, lengthened, whereas the other chlorine-oxygen bond, the symmetry, shortened. And we thought, by looking at how the chlorine-oxygen bonds and anti-periplanar lengthen, we thought this was very susceptible to a nucleophilic attack. We replaced that second water with borohydride to test this idea. And this was very exciting to us. We saw that the hydride from the borohydride arrived at the chlorine center, and this was indicating a reduction of that perchlorate. The intermediate is pretty interesting. If you look at it, the central boron, the hydrogen and the central chlorine forms a 3-center 2-electron bond, on where the orbital around the hydrogen atom forms 2 bonds at the same time, accomplishing a very stable structure for both the boron and perchlorate because they both have 4 bonds. And simultaneous to this whole thing, we observed that the chlorine and oxygen bond, anti-periplanar to the arrived hydrogen, significantly lengthened and therefore weakened. We looked at the electron density once again, and if you see, the interaction between the central boron and the hydrogen is pretty strong. The electron density is about 0.39. And the interaction between the hydrogen and the chlorine is also very strong. It's about 0.21. This once again supports the idea of 3-center 2-electron bond. We conducted additional vibrational analysis, which revealed that this is indeed a minimum on the potential energy surface. So the stretching frequency of the boron, hydrogen, and chlorine was significantly lower than the other boron and hydrogen, the 3 other boron-hydrogen bonds. This indicated a very stable interaction. And so overall, this whole picture validates our sort of proposal hypothesis. The reduction of perchlorate that was mediated by the divalent metal cations can be readily accomplished. One additional picture, if you look at the chlorine, you can see that its charge is now 1.73. It was originally 2.4, and by looking that the number decreased, it became more negative. It indicates a reduction because reduction is gain of electrons. And once again, this validated the concept of reduction of perchlorate by using borohydride. Conducted some additional wet chemistry to support what we have found theoretically from our computational results. So we attempted at first coordinating the perchlorate with divalent metal ions by reacting zinc nitrate with potassium perchlorate. By reacting them, we observed that the solubility of perchlorate increased quite a lot. So before, perchlorate alone was quite insoluble in water. It only dissolved 1 gram in 100 mils of water. However, when zinc nitrate was added, it was approximately 1 gram in 50 milliliters, so a great increase in solubility. And this, although it's only a sort of speculation, we thought that this indicated a very strong complexation between the zinc nitrate and perchlorate. So successful creation of zinc perchlorate complex. And then with this, we attempted at adding sodium borohydride to this reaction. When we did so, we observed a strong effervescence be created, which again is an indication of strong reaction. And to be more definitive, we tried to submit this for NMR analysis. And sadly, the results are still pending, so this part needs to be updated. In a nutshell, through computational methods, we found out that the divalent metal cations, the magnesium and zinc, activate perchlorate for a nucleophilic attack. And we observed that the initial reduction of perchlorate results in a novel structure containing 3 center 2 electron bond, indicating high stability. And when we added borohydride, we saw that the hydride anion arrives to the chlorine center, indicating the reduction actually occurs quite readily. And these results need further correlation with more computational work and also NMR analysis. This would be the end of my presentation, and I have to give acknowledgements to the organizing committee of this conference, the NMR Analysis Lab in South Korea, Chungnam University, and most importantly, Dr. Mark Zottola, who has mentored this project.
Well, that was fascinating, Sojin. Wow, such an important study. Let me check to see if we have questions. Let's see. I know we had a few. Scrolling down here. Joel asks, can borohydrate be synthesized on Mars, or does it need to be brought from Earth?
Oh, so that is actually one of the concerns I had. So I believe borohydride in its form has not been detected on Mars, although future studies may say otherwise. So it is likely that if this method were to be implemented, we need a bunch of borohydride chemicals transported from the Earth. However, this does not undermine our project very much. This fact is not detrimental, because if we consider the otherwise options, and that would be transporting the soil from the Earth needed for this whole agriculture on Mars, that would be much more like bigger in volume, and therefore more heavy on the cost for transportation through starships. And so even if borohydride is not native to Mars, it wouldn't be that unsuitable a solution.
All right. And Tamazan asks, are there any secondary issues of using borohydride to the environment?
This research is actually only a small portion of what I've conducted. So here's where the weakness is revealed. Sodium borohydride is actually known to be a toxic chemical. However, what my overall research tried to do was attempted using DNA as a delivery vehicle of this borohydride. And so the borohydride solution alone would not be actually probably not ideal to be implemented. But if we use DNA as the delivery vehicle, and so use boronated DNA and employ the boron and hydrogen bonds attached on that pH3 complex, that structure is actually biologically inactive, and so it isn't environmentally harmful to our human health.
Okay. Congratulations from Pateo. And Kai says, we would very much like to integrate your research into our new analog at Biosphere 2 as a fundamental science objective to transform regolith into soil. Are you familiar with Biosphere 2?
No, I'm not, but
well, it's a human-rated closed-loop system is how it started out, but I'm not certain I think Bruce McKenzie's on here. Bruce, is Biosphere 2 still a closed loop human rated system?
That is very cool.
Hello, yeah, this is Bruce. Susan, can you hear Bruce?
Yes, I can hear you.
Hello, Susan.
Hello.
Okay.
So tell us.
80s, they had about 8 people. They tried to be closed, and it is no longer closed. They are running experiments there. I believe the University of Arizona has taken it over. There's a small 3-person chamber being run by one of the previous presenters, but it's not closed anymore, as far as I know.
Great, thanks, Bruce. So Kai, please put your contact information into the chat window, and we'll see that Sojin gets that.
Oh, this is very exciting.
Yes, Kai is on staff at Biosphere 2.
Yes. Okay, next question is, would sufficient heating decompose sodium perchlorate to O2 and NaCl?
Oh yes, considering that perchlorate is a strong oxidizing agent, putting it in a combustion reaction would definitely integrate it. I'm not sure about the final product, but that would definitely be a valid reaction. However, one concern is that putting perchlorate under significant heat is very dangerous because, as I've mentioned in my presentation, perchlorate is a very strong oxidizing agent. It is used for making bombs, and so putting it in a strong heat would not be ideal in our Mars habitat, where our sort of habitat would be structured under very tight control of like vacuumized and controlled very tightly. So.
Okay, and Patrick asks, how much borohydrate might be needed to prepare a given amount of soil? For instance, 100 cubic meters?
Okay, that is the project that I am working on, and I'm sorry to say that I don't have valid results yet. However, considering that the concentration of perchlorate is actually, like I said, 1.5 to 1.7 weight percentage per in the Martian soil. And so even though it is, the number is very high as a toxin, so its toxic effect is still significant, but the amount itself is not so significant. So for now, I would just say that it wouldn't be much.
Okay, and Gary, Mars Society Australia, asks, can you leach the perchlorate out of the root zone with water?
Oh, so simply using water to wash out perchlorate, is that? Oh, I guess I can ask. Like I said in my presentation, perchlorate is very aqueous in water, and washing out, it doesn't really, maybe it is possible to do that in if the area was isolated, the contaminated area was isolated, and we put just vast amounts of water to dilute it. But that first step solution seems quite ineffective. Water would be very valuable on Mars. And second, since, like I said, perchlorate is very mobile in water solvents, we wouldn't be able to either like check its removal and be certain that it has disappeared until it wouldn't be a definitive solution because perchlorate would still remain in that water.
Okay, let's see. So I do have some contact information from Kai at B2, and I'll share that with you before we end. Sherilyn says, excellent research, excellent delivery. You give us joy. Completely agree. And so if there are no other questions, then we'll end the meeting.
Okay.
All right. Thank you. Don't disconnect, Sojin. I want to give you these contact info in the chat window.
Okay.
Okay, so let's see, one new message. Yes, please reach out to Kai.
I will.
Okay. All right. Thank you all for listening. Thank you all for being here. And please feel free to move on to the next meeting. Thank you, Sojin. Wonderful presentation. Very
Thank you.
professional. You're welcome.